As we will resume, we have computed here Zn cap W cap minus Z cap W cap the norm square is equal to by the norm 2 definition. It is 1 by 2 pi integral minus pi to pi modulus of this value at theta is, that is Z mod Zn cap W cap of theta. Zn cap W cap of theta will be equal to Zn cap of theta W cap of theta minus Z cap of theta W cap of theta the whole square d theta. This can be written as 1 by 2 pi integral minus pi to pi mod Zn cap of theta minus Z cap of theta norm closed and mod W the square here mod W cap of theta can be taken as common. Sorry, 1 minute. Mod W cap of theta, okay, 1 by 2 pi integral minus pi to pi mod Zn cap of theta minus Z cap of theta mod into whole square into square here square into W cap of theta whole square. In this relation we have W cap of theta norm mod square will be less than or equal to norm W1 norm whole square. So this integral will be less than or equal to 1 by 2 pi integral minus pi to pi. This term will come here. For this term we will write it is less than or equal to norm W1 square. So this norm W1 is a constant and we can take it common out, and W1 square we will write it here, and the rest part we will have 1 by 2 pi integral minus pi to pi modulus of Zn cap of theta minus Z cap of theta the whole square d theta. This will be equal to norm W1 square is written here, and the whole quantity is called Zn cap minus Z cap the whole square. Definition of norm 2. So since in this norm 2 we have norm Z cap is same as norm Z by earlier relation 4.38 you refer. So we will cap will be gone from here, and we will have norm W1 square into norm Zn minus Z the whole square. As Zn tends to Z, this whole quantity tends to 0 as n tends to infinity. So Zn cap W cap will be limited to, so n tends to infinity it will approach the value Z cap W cap. So right hand side is also satisfied. So as n tends to infinity the left hand side converges to Z star W cap, whereas right hand side converges to Z cap and this W cap. So for L2 of Z also Z star W cap and Z cap W cap agree in L2 of minus pi pi. Hence almost everywhere in L2 of minus pi pi agreement is written by almost everywhere. The parts 2 and 3 are also similar. I will give it in as a note, and we will leave now. We will leave part 2 and 3 now, and exercise 4.4.4. Okay, we will move to the next part, what is translation operator Rk defined in L2 of Z. Similarly, as analogous to the L1 part, we have k belongs to Z. It is defined by Rk Z of n is equal to Z of n minus k, and the linear transformation T from L2 of Z to L2 of Z is translation invariant if for all Z belongs to L2 of Z, k belongs to Z. T of Rk Z is equal to Rk T of Z. It is translation invariant. That is, if T commutes with each Rk for each k belongs to Z. As we have seen, this is similar and analogous to the earlier part as we have seen earlier. Suppose this here for B belongs to L1 of Z, Z belongs to L2 of Z, defining TB of Z. What is TB of Z? It is B star W. By lemma 4.31, this TB of Z is equal to B star W belongs to L2 of Z. That is T from L2 of Z to L2 of Z, because the image is also in L2 of Z and the input is also in L2 of Z. Moreover, this 4.34 lemma, we have this and there is a bound for b star z in L2 norm will be less than or equal to infinity. So this TB will be a bounded operator on L2 of Z, and TB is a translation invariant. This is 4.4.45. You can easily see by from the definition, or you do it individually. If there is any problem, uh, you can approach. Next we have this definition 4.38. We define the delta function, delta by delta of n is equal to, we have earlier defined for n is equal to 0, this is equal to, this whole delta will be equal to E naught. We have earlier seen delta will be equal to E naught, and this next lemma we have, suppose t from L2 of Z to L2 of Z is a bounded translation invariant linear transformation. Define b belongs to L2 of Z by b is equal to t of delta. Delta is defined as E naught. And for Ez belongs to L2 of Z, T of Z. Then for Z belongs to L2 of Z, this T of Z. This T can be represented as answer as B star Z, where B is the image of E naught or delta. So this we will write this like this, because since Ej is complete orthonormal set in L2 of Z, and we have earlier seen that every element belonging to L2 of Z can be Z belongs to L2 of Z can be written as Z is equal to summation some constant Cn E k. K belongs to Z, because Ek is a standard vectors 1 0 0 0 1 0, that like that, and we have earlier seen that this infinite summation is possible, but we have earlier seen that finite linear combination of this Ek is not possible earlier, but infinite summation is possible. So T of Ej will be an element of L2 of Z. It can be written by the coefficient Ajk Ek for k belongs to Z, for this j belongs to Ej. So we have this for some scalars a, j, k belongs to Z for each j. So this taking the inner product on both sides with the standard vectors, that is t of ej, inner product between t of ej and ek, we have this inner product summation a, j, k, e, ek here, yes, ek, comma, this ek, inner product close by earlier j comma k. By earlier for exercise 4.2.5 2, we have this the answer is the coefficient at this index k. So we have also uh, for t of ej we have written this k belongs to Z. We will change the index to I, so we can this write like this. So inner product t of ej can be written as summation I belongs to Z, um, a j denotes for ej comma I, ei, ej comma I, ei, and comma ek. The answer will be the coefficient at kth index a, j, k. So it is, we have written a, j, k. This is equal to inner product this one. And what is a, j, k? A, j, k at this using this summation t of ej of k, because ek we have known that what is ek, the standard basis vectors 1 0 0 0 1 0. So at kth stage we have what is the coefficient will be in this whole summation, we will get a vector. What is the vector, what is the component at the kth stage? Kth component will be a, j, k. So t e j of k is equal to a, j, k. That is written here, a, j, k is equal to t e j of k. By the translation invariance of t, we have a, j plus 1 k plus 1 is equal to t of e, j plus 1 k plus 1. That is written here from here. And this we know that ej plus 1 is equal to r1 translation, one translation of ej. You apply the definition of translate r1 to ej, you will get ej plus 1. The definition of the translate is written earlier, and we have this for this ej plus 1, we will represent it as r1 ej, t of r1 ej at k plus 1 the stage. So this, since t is a translation invariant, we can write this as r1 t r1 as r1 t of ej at k plus 1. So this r1 t ej at k plus 1 is equal to definition of r1 t ej of k plus 1 is equal to tej of k plus 1 minus 1 is equal to tej of k. That is written here, tej, definition of r1 tej of k. What is tej of k? We have written here tej of k is ajk. So a j plus 1 k plus 1 is same as ajk. Similarly, you can prove that for any l, repeating this l times, we will have aj plus 1 k plus 1 is equal to ajk. So z belongs to L2 of z. We can write z is equal to z of j by we can write this like this: ej infinite summation for some z of j by lemma 4.26, and boundedness of t is t of z is equal to by 4.26, and we have t of summation z uh, summation zn is equal to summation t of zn. So by applying here, t of z is equal to here this one, t of z can be written as this form: summation z of j ej is equal to, by this result we can summation t of z of j ej. This since t is linear, z of j can be taken outside, so summation we will get summation z of j t of ej. So now t of ej of n is equal to, we have proved that this ajn, we have for any l this aj plus l comma k plus l is equal to ajk. So if we apply l is equal to minus j here, so j, this changes to a j plus l is equal to a j minus j comma n minus j is equal to a j minus j a 0 comma n minus j. That is written here. A 0 രണ്ട് സൈഡിലും മൈനസ് ജെ കൊണ്ട് ആഡ് ചെയ്തിരിക്കുകയാണ്. 0 n മൈനസ് ജെ. വാട്ട് ഈസ് എ 0 n മൈനസ് ജെ? ടി ഇ 0 ഓഫ് n മൈനസ് ജെ. ടി ഇ 0 എന്താണ് ഡിഫൈൻ ചെയ്തിരിക്കുന്നത്? ടി ഓഫ് ഡെൽറ്റ, ഡെൽറ്റ ഓഫ് n മൈനസ്. ഇനി ടി ഓഫ് ഡെൽറ്റ എന്താണ്? ബി ആണെന്ന് അതിനോട്, ബി ഓഫ് n മൈനസ് ജെ. ദറ്റ് ഈസ് ടി ഇ ജെ ഓഫ് n is same as b of n minus j. Hence t t of z of n is equal to t of z of n is equal to, here we can write of n, that is summation z of j t of ej of n. T of ej of n can be written like b of n minus j. So this summation becomes here z of j t, in place of t of ej of n we write b of n minus j. What is this definition z of j b of n minus j? It is b star z of n, definition of b star z of n. For all, this is true for all n, since t is translation invariant and b is t of delta, we can write t of z of n is equal to b star z of n is equal to b star z cap inverse of n by earlier result. This is, this star cap is equal to b cap z cap inverse of n. And what is this inverse definition? Inverse definition is 1 by 2 pi integral minus pi to pi each this term b cap z cap of theta e raised to minus I n theta d theta. And uh, hence we have this can be written as a note. And this result we have to we have earlier to prove t of z of n is equal to b star z. That is here we have proved t of z is equal to b star z. And this note also you can write this this equal to this one, t of z of n. So here we have this definition 4.40. Suppose z belongs to L2 of z, for nk belongs to z. Conjugate reflection we have defined for L2 of z n, we will now define for L2 of z. Z tilde of n is equal to z of minus n cap, that is also defined z star minus 1 analogous to the result there. Then you can easily see that z tilde, since z belongs to L2 of z, z tilde can also be seen, it belongs to L2 of z. What is the condition for L2 of z? Summation mode z of n whole square will be less than infinity for each vector z. So you prove it for z tilde and z cap. You can easily prove that this one, and rk of z also, by applying the definition of rk you can easily prove. And this can be also proved, but it is in the solution manual the answer is given. And for a third part we have z star cap of theta is equal to cap definition. What is cap definition? Summation n belongs to z star of n e raised to I n theta. Z star we have defined minus 1 raised to n z of n e raised to n theta. This minus 1 can be written as e raised to I pi the whole raised to n z of n e raised to I n theta is equal to summation z of n e raised to I n plus this e raised to I pi n and e raised to I n theta will go like I n of theta plus pi. What is this one? Z of n e raised to I n theta plus pi, z cap of theta plus. So z star cap of z is equal to z cap of theta plus pi. For third one also true. And fourth one you can easily prove. Fifth one is in solution manual. And last one also you can apply cap and find it is equal to 1. So uh, one more, so this ends this section, and one more result uh, left here, we have left here for part 1 and 2. 1 minute, this part 2 and 3 I will explain in detail. Okay, thank you.